Hello and welcome to Selection Sathi. Today we will learn about graphs, one of the most important topics in DSA. We will cover graph representations, BFS, DFS, cycle detection and shortest paths. This is extremely high weight in GATE CSE and coding interviews. A graph G consists of vertices V and edges E. In a directed graph, edges have direction going from U to V. In an undirected graph, edges work both ways. The degree of a vertex is the number of edges connected to it. Key concepts include paths, cycles, connected components, and DAGs, which are directed acyclic graphs. There are two main ways to represent a graph. An adjacency matrix is a 2D array where Mij is 1 if an edge exists. It uses O of V squared space and gives O of one edge lookup. An adjacency list stores a list of neighbors for each vertex. It uses O of V plus E space and is better for sparse graphs. Most practical applications use adjacency lists. Breadth-first search, or BFS, explores a graph level by level. It uses a queue start by encoding the source node. Process each node by visiting all its unvisited neighbors. BFS guarantees the shortest path in unweighted graphs. Time complexity is O of V plus E, and space is O of V for the queue and visited array. Depth-first search, or DFS, goes as deep as possible before backtracking. It can be implemented with recursion or an explicit stack. DFS is used for cycle detection, topological sorting, and finding strongly connected components. Its time complexity is also O of V plus E. DFS classifies edges into tree, back, forward, and cross edges. Let's trace BFS from node 0 on a graph with edges 0 to 1, 0 to 2, 1 to 3, 2 to 3, 2 to 4. Level 0. Visit node 0, encview neighbors 1 and 2. Level 1. Visit 1 and 2. From 1, encview 3. From 2, encview 4. 3 is not re-enqueued from 2 since it's already visited. Level 2, visit 3 and 4. BFS order is 0, 1, 2, 3, 4. Level by level. Now DFS from node 0 on the same graph. Visit 0, go to first neighbor 1. Visit 1, go to neighbor 3 since 0 is already visited. Visit 3, neighbors are 1 and 2. 1 is visited, go to 2. Visit 2, go to neighbor 4. Visit 4, no unvisited neighbors. Backtrack. DFS order is 0, 1, 3, 2, 4. Notice the depth-first pattern. Cycle detection using DFS. Graph has edges 0 to 1, 1 to 2, 2 to 0, 2 to 3. Start DFS at 0, visit 1 with parent 0. From 1, visit 2 with parent 1. From 2, we see neighbor 0. Node 0 is visited and is not the parent of 2. This back edge from 2 to 0 confirms a cycle exists, 0, 1, 2, 0. Finding shortest path in an unweighted graph using BFS. Graph 0 to 1, 0 to 2, 1 to 3, 2 to 4, 3 to 4. Find shortest path from 0 to 4. BFS from 0, level 0 has node 0, level 1 has nodes 1 and 2. Level 2 from node 2, we reach node 4. Distance is 2. By tracking parent pointers, The path is 0 to 4. BFS always finds the shortest path in terms of number of edges. Final revision tips. BFS finds shortest path in unweighted graphs. DFS does not. Use adjacency lists for sparse graphs, matrices for dense graphs. A back edge in DFS means a cycle exists. Both BFS and DFS run in O of V plus E with adjacency list representation. For more concept videos like this, download the Selection Sathi app. Like and subscribe. Thank you.